Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over part 2 of our review series on polynomials. Let's take a look at problem 7. It says to find all the roots of the cubic equation, x to the 4th plus 64 equals 0. Now, x to the 3rd is a cube, but is 64 a cube? Well, let's check. We know 2 to the 3rd is 8. 3 to the 3rd is what? 27. 4 to the 3rd is 16 times 4, which is 64. So this is also a cube. So we're going to be using the sum of cubes formula that we discussed in part 1 of this review installment to factor this first and then see how we can proceed in finding the roots. Okay, so the factored form is a plus b times a squared minus ab plus b squared. Okay, so we have x to the 4th plus 64. The goal is to find a and b, substitute into this factored state on the right, and proceed from there. So a to the 3rd is equal to, this is not x to the 4th, this is x to the 3rd power. X to the 3rd. Okay, so a to the 3rd is equal to x to the 3rd. To get a by itself, we take the cube root of both sides as we did in number 6 of part 1 of this review installment. So we have a equals x. Let's see, we have b to the 3rd is equal to 64. To get b by itself, you take the cube root of both sides. And that ends up with b equals 4. So we plug it in here. We have a plus b is x plus 4 times a squared, x squared, minus ab, 4x, plus b squared, which is 16. All right. Now let's proceed. We can find the first root by setting this factor equal to 0. Okay, and then we have to factor this component right here. All right, so if we take out the first root, x plus 4, set it equal to 0, subtract 4 from both sides, we have x equals negative 4 as our first root. Now what do we have left? We have this piece left, x squared minus 4x plus 16. This will give us 2 more roots, okay, equals 0. Now, what we're going to do next is attempt to factor this. All right. Factorization will fail here because if you look at the options, you notice that the roots are irrational. Okay. So they're actually imaginary. Sorry. So if you have imaginary roots, then you cannot factor. It's a prime situation. But let me just show that to you. Let's just attempt to factor, assuming we weren't paying attention to the alternatives. AC is 16, B is negative 4. Now, what's 2 numbers multiplied to give you 16 and add to give you negative 4? The answer is none. There is no combination of 16 that yields 4 as a product, as a sum. Okay, so if you have 16 times 1, or 8 times 2, or 4 times 4, none of these combination gives you 4. So this is prime. So how do you solve prime quadratics? You use the quadratic formula. So the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. For this quadratic, a is 1, b is negative 4, and c is 16. Okay, so a is 1, b is negative 4, and c is 16. All right, so let's plug that all in. So we're going to have x equals negative b plus minus the square root b squared minus 4ac divided by 2a. Okay. So 2a, we have 2 times 1. All right, so let's simplify this using the order of operations. We have positive 4 plus or minus the square root of 4 times 4. Negative 4 squared is 16 minus 64 divided by 2. All right, let's keep on reducing that. So we have 4 plus or minus, we're going to subtract 16 from 64. That yields negative 48. So we have the square root of negative 48 divided by 2. Okay, now how do we simplify negative 48? Let's do that over here. Simplify negative 40, actually the square root of negative 48. So what we'll do is we will take negative 48 and decompose it. Okay, the negative comes out as an I because the square root of negative 1 is I. Now let's decompose 48. Any factor that repeats will come out as a root, just one of them. Okay, so we can take out 2. 2 goes here 24 times. Take out another 2. 2 goes into 24 12 times. Take out another 2. 2 goes into 12 6 times. Take out another 2. 2 goes into 6 3 times. All right, so these two 2's can come out as a 2. These two 2's, square root of 2 times 2 comes out as another 2. And this 3 stays behind. All right, so the square root of negative 48 can be simplified into 2 times 2, which is 4i rad 3. Okay, so let's put that back in. So we will have 4 plus or minus 4i rad 3. Now we can split the division by 2 amongst these two numbers, divided by 2 divided by 2. So we will have 2 plus or minus 2i rad 3. Okay, so let's list our roots. The first one we found was negative 4. So our roots are negative 4, 2 minus 2i rad 3, and 2 plus 2i rad 3. All right, so let's see. Option letter D is the correct answer here. All right, let's take a look at problem number 8. For problem number 8, we're doing the same thing also. We're to find the roots. All right, so here you notice you have a polynomial with 4 terms. So whenever you have a scenario like this, the first thing you want to try is to factor by grouping. Okay, so you group the first 2 together and the last 2 and see what happens when you extract the GCF. From the first 2, I can extract x squared. I'm left with x plus 2. From the next 2, I can extract negative 5. I'm left with x plus 2. Since the quantities in the parentheses are identical, that's excellent. I will factor them out, and I'm left with x minus 5 times, actually x squared minus 5 times x plus 2 that I factored out equals 0. All right, now I have x squared minus 5 and x plus 2 equals 0. I can solve this quadratic using the square root property. And this I can easily solve algebraically, okay? So let's solve the easier one first. You just subtract 2 from both sides. And your first root is x equals negative 2. And this one right here, to use the square root property, I'll isolate x squared by adding 5 to both sides. And I'll have x squared equals 5. Now I'm going to take the square root of both sides. Now, anytime you take the square root of a square, you end up with absolute value of x equals root 5. Another way to write absolute value is plus or minus. So you can write it as x equals plus or minus root 5. Okay, so our roots are negative 2, negative root 5, and root 5. Correct answer is option letter C. All right, let's take a look at problem number 9. For problem 9, we are to state the possible rational roots for each function, then find all the rational zeros. Okay, so the function we have is 5x to the third is equal to 5x to the third plus 11x squared plus 7x plus 1. All right, so first thing we're going to do, we're going to use the rational roots theorem to find the possible zeros for the function. Okay, so for the rational roots theorem, we're going to be looking for, so let's write this down, possible rational roots. The possible rational roots are the factors of p divided by the factors of q. Okay, so now we have the first term and the constant term. Okay, the leading coefficient and the constant term. One of them is p and one is q. Now this is a little bit counterintuitive, or it's kind of reverse. You will think that this is p since p is a letter, the alphabet that comes first, but no. Actually, the constant term, the last term is p, if there's a constant term, and the leading coefficient is q. Okay, so it's switched around. All right, so we're going to be looking for the factors of p divided by the factors of q. So we know that p is 1 and q is 5. The factors of 1 are plus or minus 1, divided by the factors of q, which is 5, is plus or minus 1 or plus or minus 5. Okay, so our possible rational zeros, remember it's just the rational ones that it tells us. Possible rational zeros are plus or minus 1 over plus or minus 1 is plus or minus 1, and plus or minus 1 divided by plus or minus 5, that's plus or minus 1 over 5. All right, so there goes our possible rational roots, or zeros. Now let's go ahead and find all the rational zeros. To do that, first thing we're going to do, we're going to take a look at this polynomial right here. It's a cubic with 4 terms. Factor by grouping will not work here because if you look at it, there's no the GCF. If I extract x squared from here, I'll end up with 5x plus 11, and then that's not identical to 7x plus 1. So I'm going to be using synthetic division to test out my possible rational roots. Okay, now whichever gives me a remainder of 0, by the remainder theorem, we know for a certainty that that is in fact a root or a zero of the polynomial function or a root of the related polynomial equation. All right, so first thing we're going to do is make sure we are missing no terms. No terms are missing, so we do not need a placeholder here. We'll extract the coefficients, and that yields 5, 11, 7, and 1. Now, we're going to test the possible rational zeros. Let's try -1, and we're going to carry out the synthetic division as we did in the previous part of this review series. Put a 0, add down, 5 plus 0, 5, multiply across, -5. Add down, 11 minus 5 is 6, multiply across, -6. Add down 1, multiply across, -1. 1 minus 1 is 0. That's your remainder. Since the remainder is 0, -1 is a zero of the polynomial. Okay? So we are going, this results in a partial factorization. Let's write that down, partial factorization, which is Now you have to be careful here. You're going to take the opposite of this term, x plus 1, because you have x equals -1 as a 0. So what is the factored binomial, or the binomial factor that has -1 as the 0? So you add 1 to both sides, and you have x plus 1 equals 0. This is a binomial that gives you -1 as the 0. So that's why we have x plus 1 here. Although we know that -1 is already a 0, x plus 1 times 5x squared. Now this becomes a depressed polynomial. We talked about this in part 1 of this review series. Since we're dividing by a first degree term, this polynomial has a degree reduction by a value of 1. So this is third. The depressed polynomial is going to go down by 1 to a second power. Okay, so 5x squared plus 6x plus 1. All right. Now let's see if we can factor this quadratic trinomial to the right. Okay, if we can't factor it, then we'll resort to using the quadratic formula. Okay, so let's see what we have here. AC goes on top. AC is 5 and C is 6. 1 times 5, multiply to give you 5 and add to give you 6. So we have x plus 1 times, now we're factoring this right here, 5x squared plus 6. Well, we're going to replace the 6x. Okay, we'll replace the 6x with the two numbers we got from our x game right here, -1x plus 5x plus 1. And then we're going to factor by grouping, all right? So divvy this down the center. From the first two, I can factor out an x. So let's see what we have. We're going to have, let's take out an x. 5x minus 1 is left. And then from these two, I can factor out 1. Anytime you can factor out a number, you can always pull out 1. And then, let's see, this was supposed to be a plus right here. I don't know why I put a minus. Plus 5x plus 1. And then you pause and do a check. Make sure that the quantities in the parentheses are identical, and that is the case here. Looking good. So we proceed in our factorization to get x plus 1. That's what we got before. And then 5x plus 1 is a common factor. So we have 5x plus 1 times what's left on the outside, x plus 1 times x plus 1. Okay, so that equals to 0. Now to finish it off, we just set x plus 1 to 0 using the zero product property, and 5x plus 1 to 0. Now let's solve this x plus 1 factor. Subtract 1. You have x equals -1. Now freeze for a second. We have both x, we have two x plus 1s as factors. So when you solve this, we have to state the multiplicity of this zero. So this has a multiplicity of 2 because there are two factors that yield this 0. Okay, now let's go ahead and solve the second factor. We're just going to subtract 1 and divide by 5. Okay, so subtract 1. That gives us 5x equals -1. And then divide both sides by 5. And then that gives us x equals -1 over 5. All right, so our zeros are x equals -1 with a multiplicity of 2 and -1 over 5. All right, so correct answer for number 9. Let's see. Option letter A. All right, let's take a look at problem number 10. We have to write a polynomial function of least degree with integral coefficients that has the given zeros. Okay, so we're given two zeros here. One is irrational, the other is imaginary. Now, one thing you want to note is that irrational and imaginary roots comes in conjugate pairs. Alright, so even though we're given two zeros here, the polynomial with least degree that has these two zeros must also have their conjugates as zeros also. Okay, so the zeros that we are looking at to generate our polynomial are x equals 1 plus rad 2 and its conjugate, which is 1 minus rad 2. Okay, how do you get the conjugate? You simply switch the sign of the radical piece of the irrational number. And then we have x equals 3i, and its conjugate, x equals negative 3i. You get the conjugate of imaginary numbers by switching the sign of the imaginary part. Alright, so these are the zeros that we have. Now what we're going to do, since we're looking for zeros, is we're going to set all these four equations equal to 0. Alright? Alright, so I'm going to write these proceed in a way that makes our life easy. So let's go ahead and do that. So I'm going to express this as, now let me show you what I'm doing. I'm going to subtract 1 plus root 2 from both sides, okay? And over here I'm going to subtract 1 minus root 2 from both sides. I'm going to keep them clustered together so I can use some tricks to facilitate the process. So subtract negative 3i from both sides, and then add 3i to both sides. The goal is to get each equation equal to 0. So examine how I write this. X minus quantity 1 plus rad 2 equals 0. Here we have x minus quantity 1 minus rad 2 equals 0. And then this one, x minus 3i equals 0. And lastly, x plus 3i equals 0. Okay, now let's proceed. To finish this off, we're going to use the reverse of the zero product property. Okay, so remember, when you have a zero product property, you have the factored state, you set each factor equal to 0. Now, how do we reverse that? We have each factor equal to 0. Now we are simply going to multiply all these factors together. Okay, so we have x minus 1 plus rad 2 times x minus 1 minus rad 2 times x minus 3i times x plus 3i equals 0. Alright, so it's like we're going backwards using the reverse procedures of solving polynomial equations. Alright, now let's expand this part right here. To do this, we can take advantage of the difference of squares formula. Now we have a difference of squares, a minus, let's do a plus b times a minus b. What does that expand into? A squared minus b squared. Okay, so if we do that here, you notice we have a difference and a difference, so we can't use it directly. Now, I'm going to use the associative property to reassociate the terms here so that I can take advantage of this formula. Now watch this carefully. I'm going to associate x and the 1, x minus 1, and add on the root 2. And then I'm going to associate the x and 1 again over here. And check this out. I have a minus root 2. Okay? The beauty of this is we have an a, x minus 1, plus a b, and an a, x minus 1 minus a b, a difference of squares in factored form. Okay, so let's go ahead and multiply this out. We can use this formula here because we have a minus b times a plus b again. So what does that expand into? It expands into a squared minus b squared, which is 3i squared, equals 0. Okay, so let's switch our attention back here. We're going to have a squared. A squared is x minus 1 quantity square minus b squared, which is root 2 square. All right, and then here we have, what do we have? We have x squared minus, if you square 3, you get 9. Now what is I squared? I squared is negative 1. Okay, so you want to remember that. Anytime you square I, you get negative 1 because I is the square root of negative 1. Okay, so let's switch our attention back here. X minus 1 square. Let's do that on the side here real quick. So we have x minus 1 and x minus 1. I'm going to use the box method to multiply this. So x minus 1 times x minus 1. That's look good. Let me do that again. So let me use a real straight line so it looks pretty. So we're going to do x minus 1 times x minus 1. See what we get. All right, so we have x times x, that's x squared. Minus 1 times x is minus x. Minus 1 times x is minus x. Minus 1 times minus 1 is positive 1. So it basically expands into, we have x squared minus x is minus 2x plus 1. And then what happens when you square the square root of 2? You get 2, right? The square and the squares are inverses, so they cancel each other out. So we're left with x squared minus 9 times positive 1 times negative 1 is plus 9. So we have x squared plus 9 equals 0. Now let's combine like terms. We have x squared minus 2x minus 1 times x squared plus 9. Okay, now to finish this off, we have to multiply a quadratic trinomial with a quadratic binomial. Now I'd like to use the box method here again. As I indicated in part 1 of this review installment, it's if you're multiplying polynomials where the degree is 3 or higher, it's always good to use the box method because it helps you stay organized and minimizes the chance of making mistakes. All right, so I'm going to put the bigger polynomial on the top. All right, and then we're going to have x squared plus 9 oriented vertically. Now we're going to proceed to multiply after I complete my box. This is kind of like a multiplication grid. So the first column is the squares column, the second column is the first degree column, and then we have the constant column on the right. Now let's multiply. X squared times x squared is x to the fourth. X squared times negative 2x is negative 2x to the third. Negative 1 times x squared is negative x squared. X squared times 9 is 9x squared. Negative 2x times 9 is negative 18x. Negative 1 times 9 is negative 9. All right, so let's go ahead and simplify. We're going to have x to the fourth minus 2x to the third. Now notice we have two terms of the second degree, 9x squared and negative x squared. Okay, we combine these two together, that yields plus 8x squared minus 9. All right, so this basically is our final answer. This is the polynomial of this degree that has 1 plus root 2 and 3i as zeros. So our answer, let me see, I made a mistake here. This is, oh, I left out 18x, negative 18x, so let's put that in there. That's really important. So we have, I jumped to the constant, so don't forget the negative 18x minus 9. Okay, more like it. So let's see. Answer is option, let's go back. x squared minus 2x cubed plus 8x squared minus 18x minus 9. Option letter A is the correct answer. All right, let's take a look at problem 11, the last problem in this review installment. We're asked to describe the end behavior of each function. So here is your quick guide on using the degree of the leading term to determine the end behavior. Okay, you're looking at not just the degree but also the sign. Now, if you have a leading term that is positive and with an odd degree, then you're going to have the following end behavior. So let's create our coordinate system. So let's say we have a coordinate system like this. Let's move that up a little bit. Okay, so if we have our coordinate system, we have to the right is infinity along the x-axis, to the left is negative infinity. If you're going up, that's infinity and negative infinity down here. Now for a positive odd degree term for the leading coefficient, to the right end you rise. Okay, and to the left end you fall. Okay, so that's the main idea there. You can have multiple terms here depending on the degree of your polynomial. Now, what if you have a negative odd scenario? Well, you have exactly the same thing, but it switches in the opposite direction. Okay, so everything switches in the opposite direction. It's as though you have a reflection downwards. Very similar, but in the opposite direction. So this is the right and this is the left end. This is rising for the function and this is falling. All right, so if you have a negative leading coefficient and it has an odd degree, you rise to the left, okay, and you fall to the right. And then here you can have, any kind of behavior depending on the degree of the polynomial. All right, so that's that for odd. Now let's look at even. Even though this problem doesn't ask us for even, let's go over that real quick because it's really important to understand all the cases. So for even, the interesting thing is that the left and end behavior go in the same direction. Unlike odd, they go in opposite directions, right? So this rise, fall, rise, fall. But for even, they either both rise or both fall. Okay, so rise, fall for the f of x. This is infinity. This is negative infinity. X right here, f of x. Now, if your leading term has an even degree and it's positive, so positive even degree, you're going to rise to the right and rise to the left. Remember, even degree polynomials always exhibit the same end behavior. Now, what do you think happens if you have a negative leading coefficient with an even degree? We're going to have a reflection downwards, right? Remember when you negate a function, it results in a reflection along the x-axis. So we can exploit that transformation in understanding what happens with the end behavior of this function here. All right, so with a negative even, you're going to fall to the left and fall to the right. They always do the same thing. They have the same end behavior when you're dealing with even functions. Now, for this problem, we are looking at the leading term, negative x to the fifth. What do we know about negative x to the fifth? Negative x to the fifth is negative and has an odd degree. So we are looking at this case right here. It's going to rise to the left and fall to the right. So what does that look like? How do you communicate that symbolically? Rising to the left and falling to the right. Well, rising is infinity. So the function, think about f of x as y. Okay? So y goes up and down. All right? So when you're rising, guess what? F of x is going up to where? When you're rising, it's going up to infinity. Okay? So f of x tends towards infinity as x goes towards the left. What's at the left end of the x-axis? This is your x-axis right here. What's at the left end of your x-axis? Negative infinity. So as x approaches negative infinity, the function rises or goes to infinity. Okay, so this is the left end behavior that we just described using symbolic notation. All right, now what's the right end? It falls as x goes to the right. How do we describe that? Well, falling along the y-axis, way at the bottom of the y-axis is negative infinity. So when you're falling, the function is tending towards negative infinity as x goes to the right end. What is at the right end of the x-axis? Infinity. Okay? So this statement just basically tells you that the function falls as x goes to the right, as the function goes to the right. Okay, so this is a right end behavior. Correct answer for number 11 is option letter B. Thanks so much for taking the time to watch this presentation. We hope you found it beneficial. If you have any questions or need support, feel free to post your questions on the comments section below for free support on the contents of this tutorial. Do not forget to subscribe for other great math tutorials to assist you in mastering your mathematic content. If this tutorial was beneficial to you, do give us a thumbs up. We appreciate the positive feedback. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day.